Alright, hi, my name is Kirkland. Today I'm going to do a 60-minute thermodynamic talk on the good old internal combustion engine. What is an internal combustion engine? As a couple groups said earlier, it's the engine that takes fuel and air. Fuel is the combustible material, and air is an oxidizer, compresses them in the engine itself, and the expansion of this explosion actually pushes a mechanical piston, which can be translated then into mechanical work, and can be used for energy sources, power generation, just to move any device. And it's been used for the greater part of the last century, really. And for types of heat engines, we have the external combustion engine, just as a comparison to internal combustion engines. These engines are such as steam and internal combustion engines. And for example, external we have steam engines, turbines, and Stirling engines. Which basically these engines, the combustion happens in some outside chamber than where it's actually points into mechanical work. And from the combustion chamber, it's then transported into the engine itself. The internal combustion engines, as the name implies, combustion takes place in the engine, and just some basic cycles that we've all heard of before with the thermodynamics. You have the Otto cycle, the diesel cycle, and such as jet engines, as Giselle talked about earlier. And the basic internal four-stroke combustion cycle, you have air and fuel brought into the piston cylinder apparatus. From there, it is compressed, the valves close at the top of the cylinder. Then it is combusted, driving the piston down in the power stroke, and then the fuel is exhausted. The only part that power is being generated is actually in the power stroke, and all these subsequent strokes actually rely on the power stroke to have enough momentum to transport the engine back to the power stroke. And most four-stroke combustion engines, the basic spark ignition type, can be modeled as ideal Otto cycle. Although it's not the case, the actual PV diagram can be seen here. You go from the intake to exhaust to compression and back to expansion. That's a basic simple model which I already went through right here. But the ideal Otto cycle, the compression and expansion stroke actual isotropic, which would never actually take place in a real world scenario, but it's an ideal cycle. That's how it's modeled. And the efficiency of a Otto cycle, which is we have isotropic compression from 1 to 2, constant volume heat transfer from 2 to 3, 3 to 4 isotropics and expansion, and 4 to 1 you have constant volume heat rejection. And the thermal efficiency of the cycle can be modeled as the work of the cycle over the heat added to the system, which is broken down further here to the mass and internal energies of different parts throughout the cycle itself. And this can actually be simplified into just the temperature at step 1 of the process over to step 2, 1 minus that actually. And here's the thermal efficiency of an Otto cycle. Typical values are usually between 7 and 10, and usually the higher the compression ratio, the higher the thermal efficiency. And but a higher R can lead to an engine knock, so all these factors have to be taken into consideration when actually designing an engine. You may have an engine that's somewhat efficient, but it might not, can be very unattractive to users and actually cause problems within the engine itself. And as a comparison, the diesel cycle, which is a compression ignition process, there's no actual spark plug. The fuel is ignited on just the pressure of the gas is being compressed within the cylinder. And it's a constant pressure process from 2 to 3, unlike the basic Otto cycle. And it has a lower thermal efficiency compared to the Otto cycle and the same compression ratio. But they have higher thermal efficiency in spark ignitions because the diesel engine has a much higher compression ratio. And they have very high compression ratios, ratio of 10 to 20% higher than spark ignition engines. And some basic improvements in performance on spark ignition engines mostly, and some diesel engines. You can increase the compression ratio. This will actually get more power out of the engine. You can increase the displacement, just make the engine bigger overall. this actually will increase the volumetric efficiency of the engine, and you can make the travel of air and fuel in and out of the cylinder more smoothly. Just increase the flow rate, add more valves to the engine, bigger bores on the engine, and fuel injection. You can do away with mechanical fuel adding systems and actually have a very precise fuel addition and metering processes for introducing fuel and air into your engine. Any questions?
So you compared two kind of engines, one is spark ignition and one compression ignition.
Yes, sir.
Regular known as gasoline and the diesel. So which one is more efficient?
Usually, I think diesels are over. I think they produce more power for the fuel actually consumed. Spark ignition engines usually have to rotate it, usually have to turn higher RPMs to produce the same power. But the diesel engines are also usually much heavier just because the compression ratios. You have to actually have a heavier engine with beefier components, and they're more expensive to produce. But diesels can be more efficient, much more efficient.
Any other questions? That's the end of it.